So here let's discuss a barber shop example. This barber shop is run by a German barber. So because it's a one-man barber shop, it's basically has got only one server. Uh, Cutter shop opens at 8 in the morning. So at 8 3 a.m. Uh, he has his first customer arrival, and haircut begins at 8:03. So first haircut takes 17 minutes. um, Haircut ends at 8:20. However, customer 2 arrived at 8:15. Here you can see that the barber is not free until 8:20, so the second customer needs to wait for his turn, and so on. So um, what they are doing is plotting the number of customers in this particular one server queuing system for first 100 minutes. This includes both customer waiting uh, to begin a haircut and the one already underway. So this is basically the evolution of the number of customers in barber shop for those first 100 minutes from 8 a.m. to 9:40, and the data was given in previous slide here. So here you can see that um, customer are waiting, and customers are waiting in the queue for their turn. So arrivals of the customers, we can say that okay, the times between consecutive arrivals to a queuing system, which is also called an inter arrival time. So when you are modeling this, right, or the time between consecutive arrivals of your customers, whenever you're modeling, you, you you should be modeling it as a random variable. Deterministic values, however, are not recommended. So once you collect data for let's say 1 day or first 100 minutes, so it's a very good idea to use that data and fit a distribution in that collected data. So here we can say that for inter arrival time, so you can use exponential distribution for inter arrival times. So we only need one parameter for exponential distribution, and uh, that is lambda, which is basically 1 by mu, right? So estimate the expected number of arrivals per unit time, and this quantity is also known as mean arrival time, and it's like represented by lambda. uh, right. The mean of this distribution actually comes directly, so we can say lambda is equal to mean arrival time for customers coming to the queue, and the mean of the probability distribution of inter arrival time is 1 divided by lambda, which is the expected inter arrival time. Okay. Most queuing models assume that the form of probability distribution of inter arrival times as an exponential distribution. So let's say in this particular example of barber shop, 300 customers have arrived over a period of 100 hours. So if we want to calculate lambda, that would be 300 customers divided by 100 hours. So that is uh, 3 customers per hour on average. So this lambda is basically 3, and if I want to calculate the corresponding estimate of the expected inter arrival time, so that would be 1 divided by 3 hour between customers on the average. uh, Very useful distribution, exponential distribution, for modeling inter arrival times. So here is your lambda as 1 by 3r between customers on the average, and again it has only one parameter, which is lambda. um, as it's true that for most queuing systems the servers have no control uh, over when customers will arrive, and it's true that customers generally arrive randomly. The only probability distribution with this property of random arrival is the exponential distribution. Uh, the fact that probability of an arrival in the next minute is completely uninfluenced by when the last arrival occurred is called the lack of memory property, and that is associated with exponential distribution, or it's the Markovian property. Um, this is a strange property because it implies that the probability distribution of the remaining time from now until the next arrival occurs always is the same, regardless of whether the last arrival occurred just now or just a long time ago. So as I mentioned, that it's a very useful property, and we can use it for inter arrival times for customers. uh, let's talk about the service time, or the mean service rate. So for a basic queuing system, each customer is served individually by one of the servers. A system with more than one server is called multiple server system. However, a single server system is the one which has only one server, and the cutter's barber shop has only one server, right? So when a customer enters a service, the elapsed time from the beginning to the end of the service is referred to as the service time. Service time generally varies from one customer to another. It should not be just one value, because sometimes customer are like one customer might be done quickly than the other, right? So it's a it's a very good idea to um, not just assign only one fixed value to all the customers, right? Okay, so basic queuing models assume that the service time has a particular probability distribution independent of which server is providing the service. The symbol which they are using for the mean of the service time distribution here is 1 divided by mu, which is expected service time, where mu itself um, a, is the expected number of service completions per unit time for a single continuously busy service, or expected number of service completed per unit time. Right. So in this particular example, we can assume that the expected time to give a haircut is, let's say, 20 minutes. So here 1 by mu, that is basically 20 minutes. So then mu is 3. So means that 3 customers per hour are being served. So this is how we are going to model this particular problem. So the queue is where customer wait before being served. For this barber shop, the customer in the queue sit in chairs while waiting to begin the haircut, right? The number of customers in the queue uh, is the number of customer waiting for the service to begin. The queue capacity would be the maximum number of customers that can be held in that queue or in that particular shop. Uh, so an infinite queue is one in which, for all practical purposes, an in like un here unlimited number of customers can be held there. When the capacity is small enough that it needs to be taken into account, then the queue is called a finite queue. During those time when a finite queue is full, any arriving customer will immediately leave, because the queue cannot hold that customer. In this particular example, um, it's a finite queue, and the queue capacity is 3, since the barber provides only 3 chairs for for waiting. The queue discipline refers to the order in which members of the queue are selected to begin service. The most common one is first come, first serve. However, there are other possibilities also, such as random selection, some priority procedures, or even last come, first serve. So, like randomly, you are randomly selecting people for providing service, and there is a some priority. Uh, First, last come, first serve. That would be like bangle example in for hands, right? So when you take out bangle, the last come will be the first one to go out. Okay. um in addition to that, elevator example could also be first come first sorry last come first served example. Okay. Let's talk about labels of queuing model. So to identify which probability distribution is being assumed for service time and for inter-arrival times, a queue model conventionally labeled is shown here. So this is showing me distribution of inter-arrival time. Here it's showing me distribution of service time, and here it's showing me the number of servers. So M would be my exponential distribution Markovian, and D would be my constant times. So MM1, right, that would be a single server model that assumes that both inter-arrival time and service time have an exponential distribution. Um, just another example would be MM2 model would be assuming um, both inter-arrival times and service times as an exponential distribution, but it has got two servers here. And MMS so is the corresponding model that permits any number of servers, right? MDS has exponential arrival time, M, right, first one. Then D, we have constant service time, and any S could be any desired number of servers. uh, G could be used for general independent inter-arrival time distribution or any arbitrary distribution allowed. GI, right? General independent inter uh, arrival time distribution. And for G we have general service time distribution, and here any arbitrary distribution allowed.